It's 5, so you are ready, I think. Yeah. Okay, so welcome everyone. We are here to start the first lecture of the series on the geometry and 5D SCFTs. And we are very happy to have Professor Sakura Schafer Nameki here. And she will give a series of lectures on geometry and 5D SCFTs. So Sakura she's a professor at Oxford University. She's very well known for all kinds of string realizations, recently working on F-theory and geometric engineering of 5D field theories and superconformal field theories. And this is the topic also connected to geometry she will be speaking about. So yeah, let's begin then.
Great, thank you. Thanks, Babak, for the introduction. By the way, are you recording this?
I believe it is being recorded.
Okay.
But to make sure.
Do you mind if you have any concerns?
No, I don't mind at all. It's just that some people might want to watch it at the other, untypical part of the universe. And I was just wondering. Okay, good. Thank you very much. So thanks, Babak. Thanks for the organizers inviting me to lecture on this topic. It's, I think, an exciting topic that has seen a lot of development, and I think we'll also in the next years we'll see more as we learn about these somewhat mysterious superconformal field theories. So actually, I should write down the title first. So the topic is 5D as superconformal field theories and geometry. And essentially, I will try to give you an overview of what has happened in the past few years on this matter with a slight angle more towards geometry. But in fact, we'll start off doing a lot of field theory first and then try to put it in the context of geometry. Just about the setup, I want you to ask questions, just unmute yourselves. And I also have the chat here in one sort of angle of my eye, but you should just feel free to sort of shout whenever I'm too fast or there's something that's not clear. Okay, I want to start with some motivations. So of course, you already heard lectures by Shlomo Razamat on 4D SCFTs with n=1 supersymmetry. And I think some of the ideas that came through there also tie in very well with what I'm going to talk about. Namely that many superconformal field theories in lower dimensions, lower meaning dimension D equal or less to 4, have some avatars in higher dimensions. And that will be sort of one of the guiding principles also in these lectures here, except that we'll be talking about 5 dimensions and we have n=1 supersymmetry in 5D. Okay, but what are the motivations? So superconformal field theories so as they're just writing it out once, exist in dimensions less than or equal to 6. This is a classic result by Nam. With 6 being the maximum dimension. In 6 dimensions, we have the choice of n=2,0 or 1,0. And recently, we've seen a lot of progress. Lots of progress in actually classifying these 6-dimensional CFTs. And that is the 62,0 theories actually are classified essentially by Lie algebra. So for 2,0 supersymmetry, these are basically and have an ADE classification. But then much more excitingly in the last years for n=1,0, which is the minimal supersymmetry, there's a sort of geometric classification. One that relies very much on understanding the geometry of certain Calabi-Yau spaces. And so this goes back to the work of Heckman, Morrison, Vafa plus Rodelius, and also Barbage, and many others who've refined these results. So there's essentially an understanding that we have a large class, maybe not all, but certainly a very substantial class of 61,0 theories. And there's also sort of a clear distinction between these higher dimensional superconformal field theories and lower dimensional ones, as I already hinted to earlier. So basically, there's a clear, between SCFTs in d less than or equal to 4 and d equals to 5 and 6. Namely, if you just look at sort of a gauge theory in d dimensions, right, and you look at a gauge kinetic term, so a kinetic term g m L squared, integral trace f squared d dx, then you see that g squared Young moles, the mass dimension of that is 4 minus d. So for d bigger than 4, so in 5 and 6, this is negative. So if you were to do what you might do in 4 dimensions, you write down some gauge theory, then you might find, at least naively to start with, that in fact in d equals to 5 and 6, these are actually IR-free theories. And so that potentially there's a question whether, so it's not clear a priori that there exists some non-trivial fixed points. But what this work, basically starting with work by Cyborg and then continuing with sort of other papers, has shown that in fact, or in the 90s, it was observed that in fact in d equals to 5 and 6, there are fixed points in the UV that are interacting exist, where there is a lot of evidence that they exist. And this is in particular in d equals to 5, work by Cyborg, plus Morrison, plus Interligator. Okay, so the key here is to conceptually what's different. I will hopefully be able to write slightly less strangely on this iPad. So actually it looks slightly different from the way it normally does. So hopefully it will settle down. So conceptually, what's different is indeed that one needs some way of accessing the strong coupling, right? So you need a framework. The G going to infinity limit in a quantitative way. So there are various approaches and they have various advantages, but I think so far the most comprehensive way that one can learn something about all of these theories is essentially using some geometric approach. Right, so, but let me, just because these are lectures to give an overview of what kind of other approaches there are. Of course, many of you are much more experts in that than I am. These exact calculations, localization calculations, where one can actually take a gauge theory computation and compute certain protected quantities also at strong coupling in 5D. So essentially, there are 3 approaches. One is to use exact localization, and that was essentially in the recent years pioneered by Kim Lee. in many follow-up papers. I'm not doing a comprehensive literature summary. I actually will produce some lecture notes, hopefully then we'll have all these references. The second approach that if you're talking about a superconformal field theory, you might be tempted to use is a type of bootstrap approach. And in 5D n equals 1, there are some attempts to do that, but they're somewhat limited. So limited scope. And then the third, which is what we'll focus on, is to use a geometric engineering approach where we model these theories, both the gauge theory part, but also the strong coupling in some geometric framework. And so this is what we'll focus on. So here we consider M theory on some singular geometry. And these are Coulomb geometries, threefold to be specific. And we'll get to that in the following lectures. So that's one motivation, that essentially these are not gauge series where you can sort of write down your Lagrangian and do some calculation and everything falls into place. You really need to pick your tools to really be able to get to the strong coupling limit. Now, why are these theories interesting? So you might say, okay, that's cool. You can calculate things for these higher dimensional superconformal field theories, but there's also a lore which has sort of come through in the last years, and that we can find lower dimensional CFTs by compactifications from higher dimensions, right? So that you can make something new out of something old. So perhaps not all, but certainly a vast number, a large class. And for 5D, I can be a bit more specific, a large class of lower dimensional SCFTs can be constructed by compactification of higher dimensional ones. Right, so of course, I'm starting in 6D and then going down to 4D, 5D, and so on is the strategy to pursue. And indeed, we all know that there, right, just starting with 62,0, you can do a class S construction to 4D n equals 2 and get a huge class of theories. I think Shlomo Razamat talked about compactification from 6D to 4-dimensional n equals 1 theories. What I want to basically argue for is we can start in 6D and then do a circle reduction with benefits, I call this. Sort of, it's not just putting it on a torus, but it's on a circle, but putting it in a circle, turning on mass deformation or holonomies along the circle. It could also be some twists, some automorphisms, doing some operation that is essentially compactification of a generalized sense, gives you essentially 5D SCFTs. There's no proof that this gives us a whole set of them, all of them, but certainly it gives us all the ones that we know. So that seems pretty good. Okay, so 6D SCFTs on a circle with benefits. Right, so this could be holonomies or twists. We go to 5D SCFTs. And then, of course, the goal is when can you go to 40 and so on. And then, of course, there's always then a choice. Do we actually break supersymmetry in the process? Do we retain supersymmetry and so on? So what we'll consider focus on here is to go from 6D 1,0 to 5D n equals to 1 CFTs. And in fact, in this setup, essentially, we find from such a process all the known 5D SCFTs. And so there's conjecturally, or there's at least a lore out there that we can potentially then get from the 6D classification, one for 5D. So starting in higher dimensions and understanding the lower dimensional theories is certainly a useful way of getting theories. In fact, this may or may not result in a classification, right? But it generates all known 5D SCFTs and also resulted in the construction of new ones. Okay, so that's one of the key motivations basically laid out for you. These are strongly coupled CFTs, intrinsically strongly coupled. String theory will play a key role to actually understand that strong coupling point, the UV fixed points. And the other one is it sort of gives you a map through the theory space of superconformed field theories. So we start in 6D, then we go to 5D, and so on. Now you might say, okay, so what is there to be done if you just have all the classification 6D? So you just put on a circle, you turn on some mass deformation or something, you get all the 5D SCFTs. Well, morally speaking, that is true, but in practice, there's a much more complicated enterprise. And also characterizing the properties of these theories has in itself sort of various challenges, and that's what we'll discuss in these lectures. Okay, so this is sort of as much as I want to talk about motivation. I want to now basically go and just give you a brief overview of what the lectures will be about. So you have roughly a roadmap where we're going. So in lecture 1, we'll do field theory and basically field theory what's called on the Coulomb branch of 5D equals 1. And I'll try to formulate it sort of in a slightly more modern way than you can read in the original papers by Cyborg and Morrison and Interrogator. And so this will be 5D n equals 1 gauge series and the Coulomb branch. And I will give you sort of a description of the Coulomb branch that is particularly suited to then slot into a geometric framework. Okay, so, and then another thing to discuss is the criterion for the existence of a UV fixed point. Right, and this is largely work going back to Interrogator, Morrison, Cyborg, but then also updated with very important things by Jefferson, Kim, Bafa, and Schafer. Okay, that's lecture 1. Lecture 2, we then turn to realization in geometry. So this will be the M theory realization. Of 5D gauge theories and UV fixed points. And I will give you some dictionary between the geometry and the gauge theory data, and this will connect again to sort of modeling the Coulomb branch. So modeling what we learned in lecture 1 in the context of this M theory construction. So the Coulomb branch is over CB, the Coulomb branch in the geometry. So this will tie in with resolutions of singularities in Calabi-House. Lecture 3 will go hand in hand with lecture 2, and we'll look at various refined properties, right? So things that are things such as the flavor symmetries of 5D SCFTs, and that can be 0 and 1 form symmetries, UVs, so dualities, these are called UV dualities, and rather other more refined aspects that all come from this Coulomb branch picture that we developed. And then lecture 4, I'll discuss aspects of the Higgs branch. Oops. So Higgs branch is probably the least well understood from a geometric point of view. So I'll try to explain what we do know. And most of it we know from toric models or generalized toric models, which are just basic brain webs. And then there's a question how we import that and how do we use that in the more general framework of these geometric realizations. Okay, so this will be toric and generalized toric. And then secondly, what we know about this from the geometry, more generally, this is what's called the deformation theory of singularities. Okay, so that's basically what we will be spending our mornings or your evenings with. Are there any questions, any comments? Is this what you expected? If not, this is the time to basically sign out of this call. And if this is what you expected, you should stay in. So I guess at this point you don't have questions, but I would like you to sort of give me some feedback as to how we are doing in terms of speed and so on. So this is just basically a gentle way of settling into where we're heading. And I will now start basically with lecture 1. Unless there are any remarks, comments, questions. Okay, so the first thing, as I said, lecture 1 is the Coulomb branch. Or 5D n equals 1 gauge series. And the way you should think about this is there's the Coulomb branch, and I will explain in a moment. These are some cones, they have subdivisions, and the CFT that we're trying to understand lives basically here. So the Coulomb branch is something like this, and the CFT, the UV fixed point, lives at the origin of the Coulomb branch. Now, I also said there's the Higgs branch, and the Higgs branch will essentially be something that's sort of other directions in this moduli space that go off, and the general global structure of that are not very well understood, but that's sort of one of the questions that we'd like to understand in the future better. Okay, so this is just for you to remember. Let me actually start now describing what the Coulomb branch is. So there are 2 questions we'd like to get to today. So goals. Good to have goals in life. So the goal structure today is we want to understand, so given a 5D n equals 1 gauge theory, some gauge group G plus some matter, what's a good description of the Coulomb branch, or in fact what I call later the extended Coulomb branch. And the second question that we'd like to sort of also discuss is, when does a 5D n equals 1 gauge theory have a non-trivial UV fixed point? Okay, so these are criteria that then tell us if you would not go to strong coupling, then you actually would have a 5-dimensional and UV fixed point. And here I want to be specific, a 5-dimensional non-trivial UV fixed point. Okay, so we start with so the IR, so we'll start low energies. We have a gauge group G. That could be some non-abelian factors times some U1 to the R abelian. The rank of G, I'll always denote by R. And the global symmetries of these series are, there is of course the Lorentz, or the Poincare 1, SO1, 4 in 5 dimensions, but then also an R symmetry, which is an SU2R symmetry. So these are the global symmetries, and for this amount of supersymmetry, for n equals 1 supersymmetry, we will have two types of multiplets. So we have the vector multiplets. And that has the structure of there's a gauge potential and one real scalar field and a fermion. And this scalar here will basically be the one that will sort of be the topic of today's lecture, which is what determines the Coulomb branch direction. So these are real scalars. And they're, of course, all adjoint of G-valued fields. And lambda here is in 4 tensor 2 of the is 1,4 times SU2 R symmetry, and these are symplectic Majorano fermions. So, and the real scalars and the vevs will be the parentizing the Coulomb branch. And then, of course, we also have hypermultiplets. And they have, of course, structures, so there's some representation R of G. And the hypermultiplets have the structure as they're scalars, a complex scalars, and a doublet, and a complex, and a doublet of SU2R, scalars, and fermions. And in fact, here, generally speaking, there is also, these are also acted on by some classical flavor symmetry. Right, so you have, say, n f numbers of fundamentals, and there's a classical flavor symmetry acting on them. So that gives you an additional, so I will always denote that, in fact, as GIRF. In addition, 5D SCFTs, 5D gauges, excuse me, have also an sort of one additional global symmetry for each gauge for each of these factors GI. So there's also the current, there's a conserved current, JT, which is basically star trace F wedge F. And this is often called the U1 topological current. Or the instanton U1. And the charge under this is usually referred as the instanton number. So this is conserved by the Bianchi, and that's usually to the total flavor symmetry is then GIR F times these U1T. So if you had, that actually, let me maybe put here, let's assume W log that G is simple. To start with, that the gauge would be simple, then there's basically just one U1T current. If you had multiple gauge factors, you would get one for each of these. Okay, so essentially what we'd like to study is what happens when you actually turn on these scalar fields onto vectors for the scalars in the vector multiplet. So what is the structure of the moduli space of those vacuum expectation values for these series? So the Coulomb branch is where you turn on phi on trivial, and the Higgs branch is when you turn on the scalars and the hypermultiplets. This is a real manifold generally, and this here is usually a hypercalar. So in fact, you might think that this Coulomb branch being a real manifold is relatively, it has a simple structure, but it actually already shows us some of what happens in terms of the geometry, that there are various intricate structures that appear in the Coulomb branch, which we'll then see also in the geometry re-emerge. So I want to get as quickly as possible to the Coulomb branch and its various structures and how to describe those. So on the Coulomb branch, we have at a generic point, so it's very much like in 40 equals to 2, and the Coulomb branch, the group G at a generic point is broken to a U1 to the R, where R was the rank. So we have an abelian gauge theory, and indeed, sort of, there's some effective Lagrangians for this, very similar to what we know from 40n equals to 2. So turning on these vacuum expectation values, we have some effective field theory, which has a very simple form. There's a metric Gij d phi I, which star d phi j. Right? So phi's can be essentially multi-components, right? So you have phi, the adjoints, so we can turn them along the full, all these directions in the gauge group. In fact, the keys that these are, so I'll label them phi I, or the vevs, and the scalars, and the carton. And then we have the GRJ gauge. So this for U1 gauge fields Fj. And then there's Chern-Simons type coupling Cijk over. Oops. Oh, I've done that. Okay, so, and what determines this effective Lagrangian, so is this for U1 to the R gauge theory, and the parameters are the metric Gij and the Cijks, and they're determined by a prepotential, so by the derivatives of some function f of these scalars phi I. Where f is a function, let's start with just saying these are functions of these vacuum expectation values. Phi I is the prepotential. So you know f, from that you in fact can then infer the whole effective theory on the Coulomb branch. So the prepotential, so this is my similar C, the structure of spatial geometry for 40n equals to 2. So the prepotential, in fact, has a relatively simple form that is determined just by essentially gauge group and then the matter content of the theory. And it's one loop exact, and we can just write it down and then analyze what actually the structure of the Coulomb branch is given this prepotential. So F is one loop exact and has the following form. So it is 1 over G squared, Cij so this is the classical piece, and then there's one loop piece, which comes from basically contribution again of the scalars, but then also of the phi's, but then also from the matter field. So if there are additional hypermultiplets in some representation, and I'll denote the representation by RF. We sum over all of these. We sum over the weights of these representations. So let me just write it down and then I'll explain what this is. Okay, so here basically C and D are just group theory data. So these are just trace Ti, Tj, and Dijk is cubic Casimir, so this is the killing. And that's the cubic Casimir, so this is trace. Tj, Tk plus Tk, Tj. So let me move this down because the interesting part, so this you just look up in your group theory tables. The interesting part comes from, so this is alpha, here are the roots of G of the gauge group. These are the hypermultiplet representations with weights lambda or F, and these MFs are the masses of these hypermultiplet fields. So we're summing over, again, just some representation theoretic data, but the form of this prepotential is actually going to determine then the full structure of what this Coulomb branch looks like and how it's subdivided in particular into sub-chambers. And we'll discuss this in a moment. So you'll see it's technically a function, the prepotential of these phi i's, but also if you have massive hypermultiplets, it depends on the masses. And so it really is a function of both these phi i's, but also the MFs. And the space of the phi I and MF parameters is sometimes also referred to just as the extended Coulomb branch. Right, so this includes these MF masses for hypermultiplets. Okay, so what we want to know is what is the space of the Coulomb branch, what is the structure of this? Okay, so I think there are no questions at all. I'm not sure what this means that I'm going too fast or going too slow.
Sorry, I can ask a question. I'm a little confused. How many real scalars do we have? What's the range of this index I?
So I, right? So we had let's assume that our group G is basically simple. So take SUN. So it's just the rank of these, right? So the Coulomb branch, the phi I runs from I equals 1 until R.
Yes.
Yeah. So, for example, the dimension of this Coulomb, so that's maybe a useful thing. Thanks for the question. So the dimension of the Coulomb branch, or the phi I parameters, is given by the rank. In fact, we'll go there in a second. So let's turn off. So let's look at this in a bit more detail. And actually, this will answer your question, hopefully, in this much more directly. So we just look at the, so let's turn off just the Coulomb branch, no hypermultiplied matter. So, and no MFs. Then basically, the Coulomb branch is sort of divided by places where phi comma alpha, so this quantity here goes to 0. So in fact, a chamber is determined, so one particular branch, Coulomb branch, is given by the phi's and R such that they satisfy phi alpha I is bigger than 0 for all alpha I positive roots, simple roots. Right, so once you choose positivity in your root system, let's pick that sort of a priori, where we can just choose that, and then the Coulomb branch essentially is given by phi's, and I've written it now with sort of these kind of wedge bracket, because you should really think of these as living in the dual to the root of the weight lattice, where phi, comma alpha I is positive. So can you tell me what that space is? So I'm going to throw some questions back now just to see where we are. So if you ask, if you see a mathematician on the street and you ask, oh, so tell me what is, I have a Lie algebra, say Lie algebra with some roots, and I have the space such that I've chosen some positivity on the roots, and I'm looking at the space of all the phi such that phi alpha I is bigger than 0, what would a mathematician tell you that this is? That's probably totally trivial. So for example, let's look at this for SU2. We said, right, this is happening now, so R is equal to 1. So we're just looking at R, and now we're looking at the roots are in some normalization to, and the positive roots, and there's -2. And now we want all the ones that are basically positive intersecting with alpha. So this is alpha, and this is minus alpha. And of course, then the Coulomb branch is just this. This is C. Right? So in fact, one way of characterizing C is in terms of it's just R mod Z2, where Z2 here is the wild group of SU2. And in fact, more generally, right, C is actually R to the R mod W, where W is the wild group of G. And so this is really what a mathematician would call a fundamental wild chamber. Okay. So for SU2, this was rather trivial. Of course, we've seen this in the Lie algebra courses for other groups. Let's just do one more that's a little bit less trivial. So let's pick SU3, right? And then by choosing the positivity, so that I've chosen basically these two roots to be positive, then there's sort of a half plane that says those are now the positive roots. And in fact, the ones that are, this is sort of the fundamental line chamber somewhere, so like something like this. So this is the Coulomb branch, and in fact, there are sort of the number of such wild chambers is just the order of the wild group, and it acts transitively on these. So in fact, they're all the same, so we can just stick to one of these. So that's relatively boring. So the fun really starts once you include hypermultiplets, and that's when there's some slightly more interesting combinatorial structure appearing. So let's introduce some hypermultiplets. And let's actually keep these parameters MF to be 0 to start with. We can introduce those later. So in fact, we have to look at now remember the F had these terms which went like alpha I phi I cubed, and then there were terms which we had up here, which are lambda I F phi I. where the lambda i's were the representations of the hypermultiplets. And so essentially, the way you should think about this is that these terms here will give us some further subdivision of the wall chamber into subcones. So C gets further into chambers, and these chambers are given by, again, we think of phi as basically dual object to the weights. So phi lambda r equal to 0 are the walls of these chambers. Right, and these are based from a physics point of view, these are loci where some hypermultiplets become massless. Or some states, in fact, I should say more generally, some states. So what we need to determine then is the Coulomb branch with hypermultiplets is then sort of given in terms of all the subchambers where phi lambda r is of definite sign. Yeah. So the walls are where it's 0, and then it can have either positive or negative sign, and it has to have a definite sign. And of course, within each chamber, you can always add simple positive roots, and you will stay within the chamber. So that's one condition that you have to meet, that the subdivision is compatible with that structure. So let's actually look at maybe the simplest, slightly non-trivial example. Let's look at SU3 with the fundamental. And I don't know what your preferred nomenclature for writing these is, but I'll call these weights L1, L2, L3. So the Li are the fundamental weights. And then I can write the simple roots alpha I of SU3 in terms of alpha 1 is just L1 minus L2, and alpha 2 is L2 minus L3. So this is the unit notation from Fulton-Harris. Fulton-Harris, I think. If you have another one, pick another one. So now the Coulomb branch, as we said, we need a definite sign assignment. So if I have, I know that the phi alpha I is bigger than 0. And so if I have a weight, so if lambda is a weight with phi lambda is bigger than 0, sorry, then I can always add a simple root alpha I that also has to be bigger than 0. So when I have a positive sign assignment to the weight lambda and I add the simple root to it, it needs to say positive. So this also needs to be positive. So in fact, from this you already see that not all sign assignments are consistent. Yeah, I couldn't just distribute arbitrary signs onto the weights, and that would give you a consistent subchamber or even a subchamber at all of the Coulomb branch. So if I have a positive, and I will now write this basically, so I don't want you to, this is a warning now, and you should just keep that in mind. You might think of this as, these are not Young tableaus, these are really literally just the representation graphs, right? I have L1, L2, L3, and you can think of here, if I add alpha 2, I go from L3 to L2, and alpha 1, I go from L2 to L1. So this is literally just a depiction of the weights of the representation and how the roots act between them. So if I have a sign that I sign here, so for example, if I say L3 is positive, right, I can add alpha 2 to it, I can add alpha 1 to it. So then I know that in fact, all of them have to be positive, right? So in fact, placing a plus sign on L3, I can add positive roots and I get pluses for everybody. And likewise, right, if I place actually a minus sign on the left, then in fact, right, so if I say L1 is negative, so is negative, then I can add alpha 1 plus L1, that's just minus, oops. Take minus L1, like I said, is negative, minus L1 plus alpha 1, that gives us minus L1, and then from the alpha 1 we get L1 minus L2, we get minus L2. So in fact, L2 needs to be negative and so on and so forth. So in fact, you find then that also tells you all of them have to be negative. And in fact, we can construct, if you now go and try to understand this for, say, SUN, with any fundamental, you'll find that, right, again, the representation graph will be something like this. You've got L1 until Ln. There's a condition here that the sum of all of them is actually 0 for SUN. So in fact, having the same signs for everyone is disallowed for SUN, but that's we'll relax this later to UN. So you can always impose this condition of tracelessness at the end. So you have these weights. In fact, the rule that gives the consistent Coulomb branch subdivisions are such that if you place a minus sign somewhere, that propagates to the right and a plus sign propagates to the left. Okay, so in fact, all the Coulomb branch value with fundamental matter for SUN are just given in terms of one locus where you have a sign flip from plus to minus. And what I want you to do is actually to exercise is to discuss this for SUN with the lambda 2, so the antisymmetric. Right, so you know what the weights of the antisymmetric are. So the weights are Li plus Lj with I less than j, say. Arrange them in a table just like I did for the fundamental, and then where the roots act, and then determine what actually are the rules for writing down all the consistent Coulomb branch phases. Okay, so that's a nice exercise to do, and it gives you some feeling for how this works. Okay, so what we really want to do is not just sort of one fundamental, but we want to also incorporate into this framework of these Coulomb branch phases having sort of additional flavor symmetry. So what I'll do in the next couple of minutes is just explain to you how it extends when you have, in addition to a gauge group with some hypermultiplets, also the flavor symmetry. And the way to deal with that is relatively simple. So finally, right, you want a Coulomb branch with hypermultiplets and some representation and masses. So we have some flavor symmetry in addition. And in fact, right, so what we really have is there's some representation R tensor RF. So this is where the hypermultiplets transform in. So this is the gauge representation, and this is the flavor. Right, so for example, just to be concrete, we have an SUN gauge theory with NF fundamentals. Then, in fact, the classical flavor symmetry is just U NF, just rotates these guys with the unitary representations. If we have an SPN gauge symmetry with fundamental flavor, then the GFIR is of the SO2NF group. And now I want to know what is the structure of the Coulomb branch given this setup. And the way to do it is to think of the flavor symmetry as essentially weakly gauged. So I don't want to reinvent the wheel. I essentially just think of this as to incorporate the flavor symmetry by think of it as a weakly gauge symmetry. So I just term a small gauge coupling for them and then just study the Coulomb branch for this now semi-simple gauge group. So then and apply the same. As for the case. Okay, so what, for example, so we will discuss this more generally, but let's just start with an example that's relatively simple. So we have SU3, say with 4 flavors. And now I want to say, we said this has a U4 IR flavor symmetry. And so I have now, I need to write down a representation graph. So basically I need which has labels which are weights, Li, and these are for the gauge, and then weights for the flavor. So and those I'll just label by Li flavor. Okay, so these in this case they're both unitary groups, so they just have some fundamentals. So in fact, we now have to write down a representation graph for this tensor product of a 3 tensor 4. And that's just a simple exercise. It's just a box. Let me put this down here. So what is this box? Let me just reiterate this. This is simply a depiction of the representation, and each box is a weight between these. Each of these edges here is the action of a root. So here, for example, this would be the root alpha 1, alpha 2, alpha 3, where the alpha I are now the flavor roots. So these are the GFIR roots. And then here I have the gauge roots. Alpha SU3, 2. Okay, so then the alpha ISU3 or the gauge roots. And now each entry will basically be, this will be L1 gauge plus, let me just, otherwise I'll be writing forever, LIG for the gauge ones. So this is the entry L11, so that's the first fundamental weight for the gauge and the flavor, and then I act, and let's actually abbreviate this, LIG plus LI, LJ is LIJ. So this is L11, L12, L13, L14. Let me just do this once. Okay, so that's just the diagram of all the weights in this representation. That's really by fundamentals. So there's 3 tensor 4 of gauge and flavor. And now the question is, what are the consistent sign assignments that give us all the different Coulomb Branch subchambers? So is the setup clear? I mean, I don't know. Again, there are no questions at all, so I'm not entirely sure whether I've lost anyone. Everyone is still on board and is bored to death. Either one is fine, but I need to know. So now the goal here will be find the sign assignments such that in a consistent Coulomb Branch phase. And so for the fundamentals, we already know basically that if I have a plus sign, the plus sign is sort of propagates to the left and the minus sign to the right. So now there's a sort of, it goes in both directions. So in fact, the signs, right? So what we've seen is the plus signs go like this, but of course now there's a similar thing that happens from top to bottom, bottom to top. So in fact, the plus signs propagate like this, and the minus signs propagate in the following way. Okay, so given that rule, and in fact, because now one of these is actually in a UN group, there's no trace condition that we need to satisfy. Now all of the sign assignments that satisfy that if a plus sign is placed somewhere, everything that is to the top above it or to the left of it is plus. Once you satisfy that condition, you will generate a consistent Coulomb Branch phase. Okay, so an example. So once you satisfy these, you could call these flow rules. You generate a consistent Coulomb Branch phase. So let's look at this. What kind of Coulomb Branch phases we could have? Well, of course, we could place a plus sign here at the bottom, then everything will become plus, or a minus sign here at the top, everything will become minus. The slightly more interesting ones are when sort of something non-trivial happens, right, in the middle. And in fact, let me just write down one of the things, and we'll just look at what exactly it means. So we said here, this is sort of the alpha flavor, and these are the alpha gauge. And so one consistent phase could, for example, be, I could put pluses in this way, a plus here, and then the rest minus signs. Okay? Actually, let's start with a plus sign here as well. And we can change that. And so you can see that we given a particular sign assignment, you couldn't just change the sign of an arbitrary box. So what this means is, say here, this describes one Coulomb Branch subchamber, right? And then you should think of this as like a cone and this bigger wild chamber. And now there are certain sign changes you can make. So you can flip the signs of certain weights, and that gets you to a neighboring subchamber, right? And so these are glued together by these sign changes. And so now I want to know from you, and I will wait until it's and you ask me questions until it's clear what I'm doing here. Which of these boxes can actually change signs here now in this particular diagram? Or in fact, let's do a slightly easier one. Let's start with the one that I proposed. Okay, so which box can change sign in this one? And this is a consistent Coulomb Branch phase for SU3 with 4 flavors. Which box can change sign? Of course, it could be here now quite a long time, depending on whether my audience has basically disappeared or they're still there. The right, Takanomori, the right below corner, exactly. Thank you very much. So indeed, so Takato told me this one. Yes, so you can in fact go from this one to the next phase, which is now all pluses. In fact, all here is in 1 minus sign like this, okay? And now you can branch out, and now here are the two options, right? Now you can continue, and you can either change this one and keep these pluses, or you can change this one here, pluses, pluses, and so on and so forth. And you can see that now you generate this whole set of Coulomb branch phases with all these different, and this way of depicting it, these gadgets are called, I didn't say it, but box graphs. They allow you to really very efficiently map through. So for SUN with fundamentals, it's relatively straightforward, but more complicated setups, and this becomes quite a useful tool. And we'll also see that the structure is exactly what the geometry actually will yield us in very concrete terms. So the geometry will construct for us almost exactly this object, and it will give us a little bit more information, and that's sort of the stuff that the geometry knows in addition to the gauge theory. Okay, and so of course, in the case that I initially asked, right, you can change the signs of the following guys. So you can change the sign of this, you could change the sign of that, you can change the sign of this, you can change the sign of that. And that's it. And so, so this is absolutely rubbish. So this is the plus here. So these ones that you can change the signs of, so these ones here, these are the ones, so actually that makes this important, so let me put it below. Those boxes that can change sign, these are called extremal weights. Okay, and if you're a geometer, you'll see where this is going, that extremal weights are essentially like extremal generators of the cone and the cone of curves and the geometry, and that's basically what this will become. Okay, so we have, in this way, you can now tabulate all the Coulomb branch phases for SU3 with 4 flavors. Now I want to actually look at this a bit more in a refined way, and so I would like to sort of think about one of the transitions. That's the one that goes from plus, plus, plus. Actually, I will probably skip that, and we'll discuss this when we do the geometry. I actually want to go to the question about the strong coupling. So just one comment, I'll do it verbally now, and we'll discuss it in more detail when we discuss the geometry. So these two are actually particular ones, these two signs. If I change the signs of these, in fact, the full flavor symmetry that phase sees is somewhat reduced. You can think of essentially when you change the sign of this, you're just looking at a subset of the phases within there. And so in fact, what the full gauge theory sees is just a sub-diagram. And in fact, that changing the sign of this, for example, corresponds to decoupling one of the flavors, right? So you essentially take this out of the cone of this Coulomb branch subcone, and the number of flavor roots that the gauge roots still see in sort of is reduced to just these two. So what was here actually an SU3, we were doing 4 flavor, a U4 flavor symmetry now becomes just a U3 flavor symmetry. And that we'll discuss in the geometric setting later on. Okay, so now I promised you I'll also discuss what is sort of the criterion for the existence of a UV fixed point. And that essentially goes back to Intrigligator, Morrison, Cyborg, but then was updated with very important modifications by Jefferson, Kim, Rafa, and Zafir very recently. And so we have this Coulomb branch, and in fact, what we really should be looking at is something sort of a slightly more refined structure, is what they call the physical Coulomb branch. And so essentially in these 5-dimensional theories, as you go to strong coupling, you have those EPS particles that can become massless, and you go to certain walls that become massless. But then as you go to the origin, there are also strings. So in 5D-1, there exist strings. And in M theory, when we realize them in terms of M theory, these will become strings coming from wrapped branes on particular cycles. So these are strings which have tension. Again, determined completely in terms of the prepotential as the first derivatives. And so what was proposed as the physical Coulomb branch, so C physical, is really the space C physical is the set phi in this Coulomb branch that we just discussed, where the tensions of strings are positive and also the mass squares of particles are bigger than 0. And in fact, this implies that the metric on the Coulomb branch is positive on C physical. And here it's really important to emphasize it's on the C physical. You're not requiring that the metric is positive on the whole Coulomb branch C, but actually only on this physical Coulomb branch. And that generalizes sort of away from IMS to what JKVZ have considered. So in fact, if we turn off, so also if all the masses are actually set to 0, then the C physical is also determined in terms of just the condition that phi is in C and the tensions of the strings are greater or equal to 0. And the boundary of this is actually rational. So it's given by some Ni phi I is 0 with the Ni some actually Z, I think. So these are really loci where physical particles become massless. Okay, and the theories which have a non-trivial, so in C physical is non-trivial.
Excuse me?
Yes?
So Kura, just a question, in the boundary of C physical, the Ni, they can really be integers or they have to be non-negative?
I think they can be integers because even the right, so these, I think they can be integers, they're also negative. I mean, okay, so okay, let me think about it. I will think about it, I'll get back to you. I'll put a red question here. Actually, I saw Hee-Chol here. Hee-Chol, if Hee-Chol is there, he can also answer.
Yeah, it can be negative. Yeah, it can be negative.
It can be negative, right? Yeah. Okay, thank you.
Yeah, some Ni could be negative, but not all of them.
No, but if all of the negative, you just put it at the other side, right? The negative side.
Yeah,
yes. Yeah. Great, thank you. So whenever the C figure is non-trivial, that's basically when there should be some non-trivial point. So the canonical example, I promised Shlomo that I will get to this, so I will have to get to it because he will need it for tomorrow. The example to consider is, of course, let's pick the simplest gauge group, SU2. In fact, it's healthier to think of it as SP1 with fundamental flavor. The we already said the this sort of vanilla Coulomb branch, right, with just phi is R2 mod Z2, sorry, R mod Z2. And let's assume phi is basically bigger than 0. That's all we can do. And the GFIR is SO2 NF. And if we now write down the prepotential, plugging in all the group theoretic factors, this is just going to be 1 over G squared phi squared plus 1/12, 16 phi cubed. And then sum over all the NF flavors. Sorry. Plus pi. And now at MF equal to 0, right, the tension, that way is just the first derivative, phi over G squared plus 1/2 phi squared 8 minus NF. Our phi is positive, MF are 0, that's what we get. And now we can see that if we now go to G goes to infinity, in fact, this is positive for 8 bigger than NF. So if the flavors is less than NF, and if 8 is equal to NF, T is actually 0. And if we are in the regime when NF is bigger than NF, there's no solution. So T is negative. So the good two cases are these two, and that's not a huge surprise. Also, we should check the metric. Just right, we claim the metric is then positive, and the metric is just phi 8 minus NF plus 2 over G squared, and that's bigger than 0. It has to be bigger than 0, and again for NF less than 8, that's true. For NF equals to 8 and G goes to infinity, actually the metric degenerates, and we'll discuss this in a minute. So what we learn is if we have an SU2 with NF flavors, NF bigger than 8 is an unhealthy situation, and we expect no non-trivial C physical, and in fact, no UV fixed point. When NF is less than 8, and in fact, there's a C physical and exists, and G is bigger than 0, so we expect these to be 5D UV fixed points. And then the intermediate regime, NF equals to 8, there basically the metric G at coupling going to infinity sort of degenerates, right? So it becomes entirely independent. If NF is 8, phi drops out. In fact, phi drops out. So in fact, these situations where the Coulomb branch dimension drops and the metric has a 0 eigenvalue, that's the case which hints at that there is this is sort of what's called a marginal theory or a KK theory. So these have a UV fixed point, but in 6 dimensions. So they basically decompactify to 6D. And in fact, this theory, so SU2 with 8 flavors, is the E-string theory on S1. So the 6D E-string theory. So this is the theory of M5 brains at an M9 wall, or it's an elliptic vibration of a particular making that we'll discuss at some point in the next lecture. So,
Sakura, how long do you need?
I'm almost finished. I just want to sort of give me 3 more minutes.
Okay.
Because now I don't want to stop here because this is not right. We've not just gotten to the series, so
5 more
so
minutes.
3 minutes.
The 3
So
is good.
the case of an f less than equal to less unequal to 8, right? Those are in fact these are the so-called rank 1 theories, also called Cyborg theories. The Coulomb branch, right? So basically, if you do the structure, so repeat our Coulomb branch analysis for these. We have GFIR is really it's an SP1 theory, so it has SO2 and F flavor symmetry, right? And SP1 must be SU2 is G. And the matter, the hypermultiplets, they transform in representations 2,16. And now we can play the same game, same story about the Coulomb branches. And then, so if I will cheat and I will just give you this. This is too cumbersome to draw, but also if I would draw it, you wouldn't be able to read it. So this is the representation graph. And so this is just the same as what I was doing with the bifundamentals of SUN with NF flavors. So representation graph is actually slightly more complicated, right? So this is, each one is a 16. And then here, this is the action of the alpha gauge and the alpha I, so representation of 2,16. And the alpha I are the roots of the SO16. So this is for NF equals to 8, the K. So this is the marginal theory, the KK theory. And now the claim is we can now write down all the possible Coulomb branch phases for this theory. And actually, this is probably a good place to stop. Then I think it would be good for you. So one of the exercises is determine the branch phases or box graphs for the setup. Okay, so I actually am giving you just as a sort of slight to the roots are given in terms of alpha I, Li minus Li plus 1, and then the alpha 8 is just L7 plus L8. And that's basically all you need to know. And you know how to construct, right? There are these rules. If I add positive roots or the simple roots to a weight with a given sign, that should also be an allowed sign. So I want you to think about until tomorrow what exactly now the phases are, and we'll discuss that tomorrow. Okay, so that's it. Are there any other questions? So.
Oh, could I ask again about the box graph you drew in the first example? I think the
Yeah,
3 times,
absolutely.
4 times.
Yeah.
So you said something like if you go to the extremal weights, and you said if you take the sign of the first column, the last one, if you turn it to minus, then you reduce the flavor symmetry.
That's right.
But
So,
I didn't quite get that.
Yeah, so basically, and we'll discuss this more once we get to the geometry where this becomes manifest, but in a way, so let me actually copy this guy out and discuss that. It's not the most beautiful box, but here we go. So essentially, the way this will work is the following. These were the roots of the gauge group, right? So alpha 2, alpha 1 gauge for our SU3 with 4 flavors. And the phases, the Coulomb branch phases that I write down for these are all consistent Coulomb branch phases for this theory, right? So if you now draw the whole tree of things that we started doing here, right, this one here, you will get all the Coulomb branch phases for that theory. But now, as I actually change the sign of, say, if I now change the sign of this guy here, actually that's somewhat misleading, so let me actually, let's change the sign of this. So this is sign change. So now we've made this into a minus. Then you can also think of this as, in fact, a Coulomb branch phase, a consistent Coulomb branch phase. So think of this as now some hypermultiplier. This is some particular weight that appears here, where now I can take that mass parameter for this hypermultiplier and put that to infinity, to negative infinity. I can decouple this consistently, right? This basically, this sub-diagram here, I can also now interpret in terms of, right, sending now the sign, the mass parameter. So basically this MF for this particular weight to minus infinity and decouple it. And then so in this way, what this models is also the decoupling, right? Of course, it's also Coulomb branch phase, and I can keep it at finite mass for this particular extended Coulomb branch phase with 3 4 flavors. But at the same time, I'm also describing the Coulomb branch phases. Now, if I think of these as sending those to infinity, of where I now only have these roots, so this is alpha 1, alpha 2, where here I had, so here I had the full U4 flavor symmetry, and here I would only have a U3 flavor symmetry. Yeah. So one way of actually thinking about that is I can read off also the decoupling from these extended Coulomb branch phases. It's sort of natural, even if you don't think in terms of these box graphs, right? Just that it's you've taken one of these masses, and now you can consistently decouple that, and it just models it for you in a very sort of nice way. And so, in fact, here now you can think of this as sort of how certain Coulomb branch phases for the SU3. This is for 4 flavors, and they can reinterpret this as SU3 with 3 flavors, right? With GF, just U3. Is this clear, Marcus?
Yeah, that's good. That's good. But also on attack, does it mean like in a pre-potential, if I just resolve the absolute values, the cubic contributions just drove out?
Yeah, so in the pre-potential means you're basically integrating out those massive fields. I don't know what my pre-potential is. You're just integrating out, you're putting one of these mass parameters now, sending it to minus infinity. So you don't have to do this, but you can, and then you just integrate out this particle, and then you basically decouple that hypermultiply. It's like in a brain web where you pick out one of these legs, and then you can move it to finite distance, but you can also take it to infinite distance away.
That's right. That's right. Okay, thank you.